Thank you, great talk. Next speaker is going to be through internet, Professor Ian Crawford. While you get ready, let me read his bio. Professor Crawford is an astronomer turned planetary scientist and is currently Professor of Planetary Science at Birkbeck College, London. He is presently also Senior Secretary of the UK's Royal Astronomical Society. The main focus of his research in the area of lunar exploration, including the remote sensing of the lunar surface and the laboratory analysis of lunar samples. Ian also has strong interest in the new science of astrobiology, the study of the astronomical and planetary context of the origin and evolution of life. A more detailed summary of the interests can be found from the website. His website. Professor Crawford is going to join through Skype.
Yeah.
Is it ready?
Oh, hello. Yes. Well, good morning, everybody. I guess you can hear me. I'm sorry I'm not there in person, since Sydney is one of my favourite places. And I'll say hello to people in the audience who I think are there, who I think I do know. So it's a great pleasure to be invited to give this short summary of Lunar Resources. It's too big a topic to do justice to in 20 minutes. So I'll refer you to what I'm going to say, really, I wrote up in this journal article you can see on the screen in front of you, I hope. An article, a review paper on lunar resources that was published in Physical Geography earlier this year. So you recognise the photograph. It shows the Earth and Moon together, taken by the Galileo spacecraft some years ago on its way out to Jupiter. I think the first point to say about lunar resources is it isn't at all obvious that the Moon has anything sufficiently valuable that it would justify a resource extraction industry just to obtain materials for importation into the Earth, because with one or two exceptions, everything the Moon has, the Earth has already. We'll talk about helium-3 later if we have time, but with few exceptions, you wouldn't really go to the Moon to import many things to the Earth. The way I think we should view this instead is that lunar resources can fulfill a hierarchy of applications, starting with using lunar resources to facilitate activities on the Moon itself, that's in situ resource utilisation, then moving from that to using lunar resources to for an economy within cislunar space, where the economic benefits of getting things off the Moon into cislunar space outweigh those of trying to lift them off the Earth into cislunar space. And then finally, there may be a few things that the Moon has that are valuable, that given once you've established all this infrastructure in cislunar space, it might after all be worth importing a few things directly to the Earth. So I see there's this hierarchy of possible applications for lunar resources, which I will now try and quickly go through. So this slide shows a sort of top-level introduction to the geology of the Moon. The near side is on the left, far side is on the right. And on the near side, you can see the Mare basalts are coloured in red and yellow, the high titanium basalts in red, and the low titanium basalt in yellow, and all the blue stuff is the anorthositic highland crust. So to looking at the major elements, the basalts are relatively rich at the order of 5 to 10 to perhaps even 20%, depending on the elements. They have iron, magnesium, titanium, silicon, and oxygen. They would be the high Ti lavas, that is those in red. The low titanium lavas would be the same, minus the titanium. And the anorthositic highland crust is relatively enhanced in calcium, aluminium, silicon, and oxygen, should we require these major elements. Of course, extracting these major elements from the lunar regolith in their present form would be quite an energy-intensive activity. But still, the elements are there. And I just quickly show these pie diagrams of the major element compositions of lunar soils. So Highland are relatively rich in aluminium and calcium because of the plagioclase in it on the upper left. And then the two basalts, low titanium and high titanium basalts on the lower, on the right-hand side of the diagram. I just want to make the point that if you look at the titanium concentration in high titanium mare soils, about 5 to 8%, this compares actually pretty favourably with the ilmenite-rich sands that are sometimes, well, they are exploited in Australia and elsewhere as titanium ores. So at least for titanium and aluminium and silicon and oxygen, then the Moon has a lot of these elements, although extracting them will be quite energy intensive. I want to remind everyone who's perhaps not familiar with the Moon that most of our interaction with the Moon, or all of our interaction with the lunar surface to date, is with the lunar regolith, which is this unconsolidated, but actually quite compact, but unconsolidated material several meters deep that covers the lunar surface. So when it comes to resource extraction, it is the regolith, lunar regolith, which would be our first feedstock for benefication, I suppose, which in a sense is a positive thing because it means the nature has already done quite a lot of work of grinding the lunar surface into a relatively fine-grained, unconsolidated material. Although you can see that actually from an engineering point of view, scooping up many meters, down to a depth of many meters of this material would require quite a substantial infrastructure in place on the lunar surface. The other point I want to make, well, I've just got Buzz Aldrin's boot print here in this picture for scale, is that the lunar regolith, in addition to being composed of what it's composed of, has also been soaking up solar wind particles for, well, in this case, thousands of millions of years. And so another potential resource that the Moon might have, in addition to the major elements in the rocks, are solar wind implanted volatiles, hydrogen, helium, carbon, nitrogen, some others, which can be extracted from the lunar regolith. Certainly not as much energy as it would take to extract the major elements from their oxides in the rocks, but still quite a lot because the regolith needs to be heated up to of the order of 700 degrees Celsius to degas the solar wind implanted volatiles. Anyway, I'll come back to the solar wind implanted volatiles towards the end. So I know there is a lot of talk in the literature about helium-3, which would be a solar wind implanted volatile, as a valuable lunar resource. For reasons I hope I'll get to towards the end of the talk, I actually do not think there will ever be an economic case for mining helium-3 on the Moon, and so I'm going to leave it to the end, but I will justify that statement later. Instead, I think by far the most valuable economic resource that the Moon has potentially for future space, both for in-situ resource utilization and for providing raw materials for a functioning cislunar space economy, will be water, if water is present. Now, in recent decades, it's become quite, evidence has mounted to the point where I think it's now pretty certain that the polar regions of the Moon do contain quite a lot of water, and there are several possible reservoirs of water at high latitudes on the Moon, starting with the highest concentration of water ice probably the Moon does have, which would be water ice deposits in permanently shadowed lunar polar craters. So this is a beautiful photograph. This shows the south pole of the Moon. You can see the Earth. You can see Australia. The Earth is kind of upside down from a northern hemisphere perspective, but so I guess Sydney's over here. And then this is the south pole of the Moon. So this is the Japanese Kaguya spacecraft, and the geographical south pole of the Moon is about here. And there's this large 20-kilometre diameter crater here called Shackleton, full of shadow. And there's a lot of shadow at the polar regions of the Moon because the sun is always on the horizon, and in the permanent shadow the temperature is very cold, like 20 to 40 Kelvin. And not only is water ice stable under such temperatures in a vacuum, there's now mounting evidence that water ice is present. So this is a paper from Page et al. In Science 5 years ago, and basically the Shackleton Crater, so this crater here, Shackleton Crater is there, and here is the south pole of the Moon, and then this is Shoemaker Crater, and there's a whole line of big craters. Basically the white areas show areas of permanent shadow where water ice would be stable on the surface of the Moon in these craters. And even the red and yellow areas show that even if water ice isn't stable on the surface, then it will be stable at some tens of centimeters below the surface. And then our one data point that we have is the L-cross impact into this bit of permanent shadow in the Cabeus crater in 2009, I think, from which Crawford et al. Have managed to determine a probable concentration of water ice in the superficial regolith at 5, almost 6 plus or minus 3 weight percent. Two points to make about this. Firstly, 5.6 weight percent in the lunar regolith is a lot. That's 90 litres, 90 kilograms of water per cubic metre of regolith at that concentration, and that would be a very useful amount of water. Second thing to note is the error bar is very large, so this isn't really at the 2 sigma level. This is barely a significant detection from L-cross. And this is a case for continued exploration and continued missions to the poles of the Moon to try and improve on the accuracy of the experimental error. But nevertheless, at face value, there's a potentially lot of water in these permanently shadowed craters of the Moon. Obviously tremendous operational difficulties in working in cold, permanently shadowed areas, but potentially there's a lot of water present, which in the context of a space-based economy, of course, is a source of water, obviously, and hydrogen and oxygen. And you can find these very important materials on the Moon and without having to lift them off the surface of the Earth, this would be a big advantage for a space economy. Just before I leave water on the Moon, I'll draw your attention to the infrared data obtained by the M-cubed instrument on Chandrayaan-1 spacecraft. This diagram comes from Peters et al., but basically areas at high latitude but not permanently shadowed, coloured in blue here, also appear to have concentrations of water, or if not water, then hydroxyl radicals. With a much lower concentration, of course, some with an upper limit, unfortunately, but some less than or about 800 parts per million, which would be about a kilogram of water per cubic metre. And so if this high latitude water is not extremely superficial, which it might be, but if it's been gardened into the uppermost few metres of the regolith, so the concentration in the uppermost few metres were of the order of several hundred parts per million, this would also be a useful resource of water, although you can see obviously not as much. It would be about a litre per cubic metre of regolith. In the absence of water ice on the Moon, though, it's a mistake to think that we need water ice on the Moon in order for the Moon to have a source of water. It's been known for a long time that water can be extracted from oxides in even completely dry regolith. And the most studied of these is the reduction of ilmenite. That's the FeTiO3 mineral, which is the main titanium-bearing mineral, which is found mostly in the high titanium mare basalts, of course. But reducing that with hydrogen will produce iron, which would be useful, and rutile, which is en route to making titanium, and that might be useful as well. But the key thing would be the release of water. This is a much more energy-intensive reaction, and there are lots of similar reactions. There's a review here by Taylor and Carrier in 1993, who identified 20 different processes for extracting oxygen from lunar regolith. They're all quite energy-intensive, and if the Moon has water ice at the poles, that would be a far preferable source of water on the Moon. Just for completeness on volatiles on the Moon, I want to mention pyroclastic deposits. These are volcanic glasses, essentially. These are the famous orange soil uncovered at Apollo 17 landing site. You see it here. These black areas around presumed endogenic craters on the Moon. This is in the far side basin Schrödinger, but this black halo is thought to be the same. These pyroclastic deposits, volcanic glasses, are also thought to be quite water-rich, up to a level of about 0.1 weight percent. So that would be 1,000 parts per million. So that would be comparable to the concentrations of water that you get in these blue areas of high latitudes elsewhere on the Moon. So potentially pyroclastic deposits at low latitudes might also be a source of volatiles on the Moon. But solar wind implanted volatiles, this is from the, a review by Fegley and Swindle, I think, 93. I should have put the reference here. Concentrations of solar wind implanted volatiles which are degassed if the regolith is heated up to the order of 700 degrees Celsius. So here are the concentrations in micrograms per gram, and this is how much you get from a cubic meter. And so you can see in grams, actually. So you can see, actually, you have to process a lot of regolith to extract these solar wind implanted volatiles. But nevertheless, some of them could be useful. Hydrogen would be useful because hydrogen is a useful reductant for oxides if you want to run this kind of reaction. Nitrogen could be useful if we imagine a distant future where people stop to plant plants on the Moon, lunar agriculture. Sources of nitrogen and local sources of nitrogen and carbon could be useful. The Moon is generally deficient in those, but they do exist as solar wind implanted volatiles, as does helium, and as does helium-3. Now, I feel I should say a word about helium-3. Because often one hears about the Moon being rich, in inverted commas, in helium-3, and helium-3 being a tremendous possible fuel for future nuclear reactions. I'm afraid I don't buy this argument. Firstly, helium-3 is not abundant on the Moon. It exists at an average concentration of about 4 parts per billion, so that would be 4 nanograms per gram. So to get a significant quantity of it, a huge amount of regolith will need to be processed, and that means heating it up to 700 degrees Celsius, separating all the solar wind implanted volatiles from it, separating the helium-3, shipping the helium-3 to Earth, where if you could do that in principle, there is the nuclear fusion reaction at the bottom. Deuterium plus helium-3 goes to helium-4 plus a proton, and 18.4 MeV of energy is released per reaction. Except that this particular fusion reaction has not been demonstrated yet on the Earth. It's not one of those that are currently being investigated for nuclear fusion power sources. They're investigating deuterium-tritium, which is far easier to get going, or deuterium-deuterium. So there's no real work being currently done on deuterium-helium-3 or helium-3 fusion for electricity production. So there isn't yet a demonstrated market anyway for lunar helium-3 until nuclear fusion reactors are demonstrated to work that can actually use helium-3 as a fuel. So it's probably a bit premature to consider digging up the lunar regolith as a source of helium-3, since we don't have the appropriate nuclear fusion technology yet. Still, if you do, this map of the Moon shows where helium-3 is most concentrated. This is the Sea of Tranquility. This is Oceanus Procellarum. These are the high titanium mare basalts, which, for reasons I don't have time to go into, preferentially concentrate helium-3. But even then, well above the average of 4 or 5 nanograms per gram, but even up to the most plausible concentration, you're still looking at 20 parts per billion in these areas of the Moon. Although just note, they're quite small areas of the Moon, Sea of Tranquility, Oceanus Procellarum. It's not like the whole Moon has these high concentrations of helium-3. And these limited areas have finite extent, of course, which means that helium-3 is a non-renewable resource, so it's not panacea. Once you've mined it from these areas, it's gone. So I have a lot of problems with helium-3, which I don't have time to go through this slide, because I think I've only got 5 minutes left. You can read it if you have time, but you'll find it all in that article I wrote for Progress of Physical Geography, and all the numbers are justified there. But I just want to draw your attention to the final bullet point, which to my mind is the kind of nail in the coffin of helium-3 as an economic resource on the Moon. It's easy to do a back-of-the-envelope calculation and prove that if you consider the same efficiency of extracting helium-3 rest mass into energy in a power station with the efficiency of converting electricity into sunlight into electricity with solar cells, and it doesn't matter what you pick, but if you say you pick 20% for both, so if you assume both processes have the same efficiency, then you can calculate that you only have to expose solar panels on a square metre of the lunar surface for 1.5 years, and that would collect all the energy you get from extracting all the helium-3 from the regolith underneath that 1 square metre down to a depth of 3 metres. So, but of course, your solar panels you could keep there forever, and this helium-3 has been used up once you've mined it. So, really, if you want to use the moon as a source of energy for the Earth, and I'm not convinced that we would need to, but if we did need to use the moon as a source of energy, actually it'd be far more efficient to coat the lunar surface in solar cells and beam the energy to the Earth than it would be to dig up hundreds of square kilometres of regolith every year and extract the helium-3 from it and then physically transport the helium-3 to the Earth. So having been rather dismissive about lunar helium-3, we can go back and ask, is there anything on the moon that might be sufficiently valuable to import to the Earth directly? There are a couple of possibilities. Rare earth elements are an increasingly important resource. Of course, the Earth does have a lot of rare earth elements, despite the name, and you wouldn't obviously go to the moon to mine rare earth elements. Unless you had a significant lunar infrastructure in place, sort of rendering it economical. But nevertheless, if you look at the picture on the left top, the area coloured in yellow and red in lunar geologists recognise this as the prosolar and creep terrain. It's enhanced in thorium and uranium, and that map is actually a thorium map. But these creep-rich materials on the moon are relatively enhanced in rare earth elements, and the concentrations of rare earth elements in the high creep materials in this area of the moon do kind of approximate the levels of rare earth elements in some of the poorer grade terrestrial rare earth element ores. So if the Earth ever did need an extra source of rare earth elements, possibly because mining them on the Earth becomes too environmentally destructive, there is a potential source of rare earth elements on the moon. Was that a timer going off?
Yes.
Okay, so I just, since I want to say something about asteroids, obviously some asteroids are rich in, the metallic asteroids are rich in iron and nickel, of course, but also in the platinum group elements. And there is an argument that you would mine, that this would require asteroids. Asteroids would be an attractive resource for these materials. I just want to draw attention to the fact that the moon has a lot of crashed asteroids on it. And it will have a lot of crashed nickel-iron asteroids on it. And I think we know where they are because they show up in the magnetic anomaly maps. And there's a picture here I took from a paper by Mark Wazorek, which I ought to have referenced. But basically, these magnetic anomalies on the moon are areas where plausibly remains of crashed metallic asteroids can be found. So actually, the moon may have source of nickel-iron, concentrated nickel-iron and siderophile elements. You might not have to go to asteroids to obtain these materials because the moon might have them, as well as rare earth elements and water and other things. So this is the economic argument for wanting to go to the moon. You're probably familiar with the energy difference of getting stuff off the surface of the Earth to Earth's orbit compared to getting from the moon's surface to Earth orbit. So this is the economic advantage of wanting to go to the moon. Kind of things you might want to use lunar materials for in cislunar space might be, if the future world economy requires a lot of sunlight, satellite solar power stations will be cheaper to build using lunar materials and launching them from the Earth. From a scientific point of view, large space infrastructure, scientific infrastructure like large space telescopes might also benefit from the use of lunar resources. Just 2 more slides, but I just wanted to very quickly, I know there have been a lot of talk about asteroids in this meeting, and I just think it's put to pause and compare the moon and asteroids. So, advantages of asteroids is they're small, of course. This is Gaspra. They have negligible gravities. Some of them are easier to reach in terms of energy than the lunar surface. But of course, they have and some of them can periodically get close to the Earth. But they do have, that bell sounded very, very loud, but I'm almost finished. Many of these near-Earth asteroids are not always near the Earth, of course. Their orbits sometimes get close to the Earth, but then they get quite distant from the Earth, and they have quite long synodic periods. So this may make operations not so attractive for near-Earth asteroids. the other thing to notice, if you're after iron, nickel, and the platinum group elements, you go to one kind of asteroid. If you're interested in volatiles, you go to another type of asteroids. You've got lots of asteroids. You have to be farming for all these different materials. The Moon, on the other hand, is uniformly close. It's always at the same distance. It's always only 3 days away from us. It has geological processes which have enhanced the concentrations of many useful materials, including water ice, aluminium, titanium, rare earth elements, uranium. Contains crashed asteroids that may be a source of iron and platinum group metals as well. So you might not have to go to asteroids for those. And it lends itself to the gradual bootstrapping of a surface infrastructure. And this is my last slide, in a way that I think asteroids perhaps don't. So I think the way to find out whether the Moon has got economically useful resources is to explore it more fully than we already have. I think that would argue for setting up a research station or research stations similar to those we have in Antarctica. But I also think, because Antarctic-style research stations on the Moon will require in-situ resources in order to keep them going, there's a bootstrapping process here where space exploration requires in-situ resources. In-situ resources makes more exploration. Eventually, the in-situ resources infrastructure can mine more resources than the scientific infrastructure needs. Therefore, it has a surplus which it can then sell to other potential users of lunar materials in cislunar space, and the process could be bootstrapped from there. Thank you very much.
Thank you.